Okay, so let's begin our discussion of vectors. You'll have to bear with me, this is one of the more mathematical chapters, but this chapter really forms the foundation for the entire class, and honestly for a lot of your future in science and engineering. Vectors are going to be extremely important. Examples of vectors include velocity, acceleration, force, momentum. All of these things we're going to be talking about all the time, so we need to really make sure we understand this chapter well. We have a quick video here that shows a simulation of a fluid, and we can see all the arrows drawn in this simulation are examples of vectors. They're denoting both the magnitude of something but also the direction. So you can ask me more about the simulation in office hours. Okay, so our goal here is to describe physical quantities. Often, we only need one piece of information to describe something, right? The temperature outside is 79 degrees Fahrenheit. That's all we need to know, right? Just one piece of information. And so we can do that with what is called a scalar, right? Just one piece of information is needed. And we can look at a map of the US, for example, and see that, okay, over in Chicago it's 78, but over in California it's 84 degrees, right? Every point in space has some temperature, but if just one number is needed. But in other cases, you need more than one piece of information. For example, wind velocity, right? If you were trying to land an airplane into the wind, it wouldn't be that helpful for me to tell you, okay, the wind is 20 miles per hour right now. You would need to know that, okay, the wind is 20 miles per hour east. Okay, so you need more than one piece of information. So to describe wind velocity, we need a vector. Okay, we have an example of that on the bottom right here is a map of the US showing the wind speed at every location. The wind velocity at every location, where an arrow points in the direction of the velocity of the wind, and the length of the arrow and also the color of the arrow denote the magnitude of that velocity. Right, so over in the west coast, you see the red arrows. That corresponds to wind speeds of about 20 meters per second, where maybe over by Chicago, you see the blue arrows. That denotes a wind speed of about 5 meters per second. And the direction of the arrow tells you the direction that the wind is moving. Okay, so we have more than one piece of information, and a arrow is a natural way to draw that that quantity. In other cases, you need even more pieces of information. You need to know 3 pieces of information to tell the location of an airplane, right? You need both the latitude, the longitude, and the altitude. You need those 3 pieces of information to precisely define the location of an airplane. Okay, so we'll need a vector to do that. Okay, a little bit more about scalars. Again, anytime you can describe something with just one number, that's a scalar. So we talked about temperature. Other examples include time, mass, density. And the nice thing about scalars is you can add them and subtract them and multiply them in the normal way that you are used to, right? If you have a 3 kilogram object on this scale, and I add to that a 2 kilogram object, the scale should read 5 kilograms, right? Those numbers add in the normal way. Things are going to be a little bit different with vectors. Okay, so with vectors, again, anytime you need to describe something that has more than one number associated with it, you need a vector, right? Vectors have both a magnitude and a direction. So something like displacement, I traveled 3 meters east, right? That's an example of displacement. It tells you how far you've traveled and in what direction. Force is a vector. I'm applying a force of 20 newtons in the plus y direction. A velocity is an example of a vector. Right? These all have a magnitude and a direction. Right? The airplane could be traveling at 300 meters per second in a direction 30 degrees east of north. All right, so 300 meters per second, that is the magnitude of my velocity. That's telling me how fast I'm moving, but I'm also telling you the direction. That's what makes it a vector. Okay, for a displacement example, you could say I traveled 5 miles west. 5 miles is a magnitude, right? That's how far I traveled. West is the direction. That's what makes it a vector. Okay. It turns out we're going to need different techniques to add, subtract, and multiply vectors. Right? So if I went on this trip all over Florida, I couldn't just tell you I traveled, 500 miles. You wouldn't know where I ended up, right? But if I told you I traveled, 100 miles due east, and then I traveled, 50 miles southeast, and etc., and if I told you that all very precisely, you could figure out that I traveled along this path and I ended up here in Gainesville. And then my resultant vector, or how far away am I from where I started, would be this vector r. Okay, that's an example of adding vectors where direction matters. Another nice example is with velocity. If I'm on a boat, and as far as I'm concerned, I'm just rowing this boat directly across this river, right? I think my velocity is in this direction, but in reality, the river is flowing really fast in this direction, right? If I was in a drone, if you had a drone and you were looking down on me in this boat, you wouldn't see me moving directly across the river. You would see me moving in this direction, right? I'd be both crossing the river, but the river would also be dragging me downriver, right? So you would see this kind of angled path for my actual path that I'm traveling in. So my actual velocity direction would be a combination of the velocity I think I'm traveling and the velocity of the river, but I'm not adding those together, right? If this is 3 miles per hour and this is 4 miles per hour, I'm definitely not moving at 7 miles per hour. I can't just add those together because I'm moving at some angle relative to those, right? So we have to learn how to add vectors. Okay, a little bit more about vectors here. Just symbolically, we are going to denote a vector with a symbol, for example, d. Could be for a displacement vector, for example. So we have a symbol and we draw above that an arrow. That tells us it's a vector. So when I, in lecture, draw a vector, you're going to know it's a vector because I've drawn an arrow above it. In the textbook, it's also going to be bold. I can't really do that with my handwriting, but it's going to be, so just the arrow above a symbol is going to tell you it's a vector. If you want to draw a picture of a vector, the natural way to do that is with an arrow. So if I move from here to here, right, if I want to draw my displacement vector, I'm going to draw a vector, an arrow with tail starting where I started and pointing to where I finished, right? That arrow has a tail and a head, and that's going to be a nice picture. It's going to help me figure out what happened. Okay. If I want to tell you the magnitude of a vector, symbolically, typically we would either just write the same symbol, but just not bold and without the arrow above it. Right? That tells you that I'm talking about the magnitude and not the actual vector. Right? So d could be, maybe it's a velocity vector, and maybe I'm moving 20 meters per second east. Writing d here would just be 20 meters per second. Right? We'd be forgetting about the east. Another way to do that, to talk just about the magnitude, is to draw these two parallel lines around my vector. Right? Something like writing it's the absolute value of a vector. That's telling me I only want the length of the vector. I only want the magnitude. I don't want the direction. Okay. And finally here, just a quick point, a vector can never be equal to a scalar. So if I have a vector A, right, so I know it's a vector because it has the arrow above it, is equal to 6 meters, that has to be a wrong statement, right? Because 6 meters is a scalar, it has no direction, right? So for this to be true, it would have to be A is equal to 6 meters east, or A is equal to 6 meters in the plus x direction. So I'm going to teach you later the proper notation for also writing down the direction. But just to let you know, you can never have a vector equal to a scalar. Just another quick example, again, of a displacement vector. Here is some example where I'm moving from a campsite at point A to this lake at point B. And I could travel, this path, or I could travel this path or some other path, or I could go all the way around somewhere and end up at point B. It doesn't matter what path I take. The displacement vector is going to be an arrow that starts, the tail of it is where I started, the head of it is where I finish, and the arrow points in the direction I traveled, and the length of that vector is just going to be how far away am I when I finish from where I started. Right, so that's an example of a displacement vector. Okay. A few extra points here. We're going to talk about some vector rules. First of all, I could have two vectors, vector A and vector B, and, let me go back here. Vector A could be a vector of some length pointing in some direction. If B is another vector with a different length, right, but it's pointing in exactly the same direction, I can say that B is parallel to A, they're pointing in the same direction. The same thing with this example over here. A and B are both pointing in exactly the same direction, they have different magnitude, but they're parallel to each other. Two vectors can also be anti-parallel. Right? If A and B point along the same line but in opposite directions, they're anti-parallel. Right? A is pointing 180 degrees different direction from B. They're anti-parallel to each other. One of the most important rules is what happens when you consider the negation of a vector. Or what if I have a vector A and I multiply that vector by -1? Right? If I have negative A, that's a vector of exactly the same lengths. Right? Both of these vectors have exactly the same lengths, but vector -A points in exactly the opposite direction of vector A. So vector -A is anti-parallel to A. Okay. Two vectors that are different vectors can be equal to each other. Right? Vector A and vector B both have exactly the same magnitude and they point in exactly the same direction. That means they're equal to each other. Same thing over here. Both A and B have exactly the same direction, they're pointing, and they have exactly the same magnitude, so they're equal to each other. Finally, two vectors can be orthogonal to each other. Right? Orthogonal is another word for perpendicular, or it's saying that two things are 90 degrees apart. Right? So in this case, vector A and vector B are 90 degrees apart from each other. Okay, so those are some important rules that we can just keep in our minds when we're talking about vectors. And finally, let's talk about multiplying a vector by a scalar. Right? Multiplying a vector by just a number. So as an example of this, let's go back to our example of this displacement vector where I'm starting at the campsite at point A, and you could consider walking all the way to the lake. Right? It doesn't matter what path I take, but I have some displacement vector that points from A to B, right? And I can denote that like this: D with an arrow above it, and then with a subscript AB just to let me know which displacement vector I'm talking about. And then let's say I walked 3/4 of the distance from A to B. All right, so I started walking towards the lake, but I didn't get all the way there. Right, 3/4 is equivalent to 75%, or 0.75. So what does that mean? What does it mean for me to say, as a vector equation, what is 0.75 times my original vector? Well, we can see it in the picture over here. If I multiply this vector, d from A to B, by 0.75, I get a vector which is pointing in exactly the same direction, but is 0.75 times the size, right? It's 3/4 the size. Right, it's not as long. Right? If I had multiplied d from A to B by 2, I would have ended up, way up here somewhere. Right? That would have been, maybe call that point D. So d from A to D is equal to 2 times d from A to B. Okay, so when you multiply a vector by a positive number, you get a vector that points in the same direction, but is a different length, so it has a different magnitude. Or you can multiply it by 1 and you get exactly the same vector. Okay, so in general, again, if I have a general equation given by this right here, right, b is equal to alpha times a. If alpha is some positive number, then b is going to just point in the same direction as a, but be a different length. Okay, and the magnitude of b is just going to be that number times the magnitude of a. Okay. Similarly, if alpha is a negative number, right, b and a are going to point in opposite directions. Right, the negative is going to make b point in the opposite direction, right? And so if I multiply a negative number times a, I'm going to get a vector b which is anti-parallel to a. Right? To see this more clearly, we can look at this example on the bottom. I start with vector a. It has a magnitude of 1.5 and it's pointing to the right, or we could say in the plus x direction. If I multiply a by 2 to get vector b, right, that's what I'm doing right here, 2 times a is vector b. b is twice as long as a. It points in exactly the same direction. Right? And I can see that the magnitude of b is 3, where the magnitude of a was 1.5. And finally, I could ask, what if I multiply a by negative 2? If I multiply a by negative 2, I get vector c, which points in the opposite direction. Right? That's what the negative sign did. And the 2 is making it twice as long. Right? So vector c is twice as long as a. Right? The magnitude of c down here is just 3. Right? It's twice as long, but the direction is in the opposite direction. Okay? And that's it for this video. In the next video, we'll learn how to add vectors.